Electromagnetism has a rich history that dates back centuries, with key discoveries and developments shaping our understanding of this fundamental force of nature. One of the earliest observations of electromagnetism can be traced back to the ancient Greeks, who discovered that amber could attract lightweight objects when rubbed. This phenomenon, known as static electricity, laid the groundwork for further exploration into the relationship between electricity and magnetism. In the 18th century, significant progress was made in understanding electromagnetism. In 1820, Hans Christian Ørsted conducted an experiment that demonstrated the connection between electricity and magnetism. He observed that an electric current flowing through a wire could deflect a nearby compass needle, revealing the magnetic field generated by the current. This discovery marked the beginning of the field of electromagnetism and paved the way for future advancements in technology. A pivotal moment in the history of electromagnetism came with the formulation of Maxwell's equations in the 19th century. James Clerk Maxwell's equations unified the theories of electricity and magnetism, showing that these two forces were interconnected and could be described by a set of mathematical equations. Maxwell's work laid the foundation for the study of electromagnetic fields and waves, revolutionizing our understanding of light and other electromagnetic phenomena. Today, electromagnetism plays a crucial role in various aspects of our lives, from the technology we use to the natural processes that govern our world. The history of electromagnetism is a testament to human curiosity and ingenuity, showcasing how our exploration of the natural world has led to groundbreaking discoveries and innovations that continue to shape our modern world. Fundamental concepts of electromagnetism. Electromagnetism is a fundamental force of nature that governs the behavior of electrically charged particles. At the core of electromagnetism are several key concepts that form the basis of our understanding of this phenomenon. One of the fundamental concepts of electromagnetism is the idea of electric charge. Electric charge is a property of matter that can be positive or negative. Like charges repel each other, while opposite charges attract. This simple principle underlies the interactions between charged particles that give rise to electric and magnetic fields. Another important concept in electromagnetism is the notion of an electric field. An electric field is a region of space around a charged object where other charged objects experience a force. The strength of the electric field is determined by the magnitude of the charge creating it and the distance from the charge. Magnetic fields are another crucial aspect of electromagnetism. Magnetic fields are produced by moving charges and exert a force on other moving charges. The interaction between electric and magnetic fields gives rise to electromagnetic waves, such as light, which propagate through space at the speed of light. Quantitatively, electric and magnetic fields are described by mathematical equations known as Maxwell's equations. These equations, formulated by James Clerk Maxwell in the 19th century, unify the theories of electricity and magnetism and provide a comprehensive framework for understanding electromagnetism. In electromagnetism, the concept of electromagnetic induction is also significant. Electromagnetic induction occurs when a changing magnetic field induces an electric current in a conductor. This phenomenon is the basis for the operation of electric generators and transformers, which are essential components of modern electrical systems. Interesting fact, the speed of light, which is approximately 299,792,458 meters per second in a vacuum, is a fundamental constant that arises from the relationship between electric and magnetic fields in Maxwell's equations. Another interesting aspect of electromagnetism is the electromagnetic spectrum. The electromagnetic spectrum encompasses a wide range of frequencies, from radio waves with long wavelengths to gamma rays with short wavelengths. Each region of the spectrum has unique properties and applications, such as communication through radio waves and medical imaging using X-rays. Overall, the fundamental concepts of electromagnetism provide the foundation for understanding the behavior of electric and magnetic fields and their interactions. From the principles of electric charge to the mathematical formalism of Maxwell's equations, electromagnetism is a fascinating field that underpins many aspects of modern technology and natural phenomena. Electromagnetism plays a crucial role in various natural phenomena, showcasing the intricate interplay between electric and magnetic fields in the world around us. One fascinating application of electromagnetism in nature is the migration of birds. Birds, such as pigeons and homing pigeons, have been known to navigate using Earth's magnetic field. They possess tiny magnetic particles in their beaks that act as a compass, allowing them to sense the Earth's magnetic field and orient themselves during long-distance flights. This remarkable ability demonstrates how living organisms have evolved to harness the power of electromagnetism for navigation. Another intriguing example of electromagnetism in nature is the phenomenon of bioluminescence. Certain marine organisms, such as jellyfish and fireflies, produce light through a chemical reaction that involves the manipulation of electric fields within their bodies. This natural light display serves various purposes, from attracting mates to deterring predators. The intricate relationship between electromagnetism and bioluminescence highlights the diversity of ways in which living organisms utilize this fundamental force. In addition to animal behavior, electromagnetism also plays a role in plant growth. Plants have been found to respond to changes in electromagnetic fields, with studies suggesting that magnetic fields can influence seed germination, root growth, and overall plant development. This sensitivity to electromagnetism underscores the interconnectedness of living organisms with their electromagnetic environment. Furthermore, electromagnetism is integral to the functioning of Earth's climate system. The interaction between the planet's magnetic field and solar radiation gives rise to phenomena such as the auroras, which are colorful displays of light in the polar regions. These awe-inspiring light shows are a visual manifestation of the complex interactions between Earth's magnetic field and charged particles from the Sun. The study of electromagnetism in nature continues to reveal the intricate mechanisms by which living organisms and the environment interact with electromagnetic forces, shaping the world we inhabit. Electromagnetism plays a pivotal role in shaping the technological landscape of the modern world, with a myriad of applications that have revolutionized various industries. One fascinating application of electromagnetism in technology is magnetic levitation, maglev trains. These high-speed trains use powerful electromagnets to lift the train off the tracks, reducing friction and allowing for faster and smoother travel. The fastest maglev train, the JR Maglev MLX-01, set a world speed record of 375 miles per hour, 603 kilometers per hour, during a test run in Japan, showcasing the incredible potential of electromagnetism in transportation. Another remarkable technological advancement enabled by electromagnetism is magnetic resonance imaging, MRI. MRI machines use powerful magnetic fields and radio waves to create detailed images of the body's internal structures, aiding in the diagnosis of various medical conditions. It is estimated that over 36 million MRI scans are performed annually in the United States alone, highlighting the widespread use of this technology in healthcare. Electromagnetic induction is another key concept that underpins many technological innovations. Electric generators, such as those used in power plants, rely on electromagnetic induction to convert mechanical energy into electrical energy. The largest hydroelectric power plant in the world, the Three Gorges Dam in China, has a total installed capacity of 22.5 gigawatts, showcasing the immense power generation capabilities of electromagnetism. In the realm of communication technology, electromagnetism plays a crucial role in the operation of antennas and radio waves. The global mobile industry is projected to reach over 5.8 billion unique mobile subscribers by 2025, highlighting the pervasive use of electromagnetic technology in the telecommunications sector. Electromagnetic interference, EMI, is a common challenge in electronic devices, where unwanted electromagnetic signals can disrupt the proper functioning of equipment. The global market for electromagnetic compatibility, EMC, testing is expected to reach $3.8 billion by 2026, driven by the increasing demand for EMC testing services across various industries. Quantum computing is a cutting-edge technology that leverages the principles of electromagnetism to perform complex calculations at speeds far beyond traditional computers. Quantum computers rely on superconducting qubits, which are tiny circuits that exhibit quantum behavior when cooled to extremely low temperatures. Google's quantum computer, Sycamore, achieved quantum supremacy by performing a calculation in 200 seconds that would take the world's fastest supercomputer 10,000 years to complete, demonstrating the transformative potential of electromagnetism in computing. The field of electromagnetism continues to drive innovation and technological advancement across diverse sectors, shaping the future of our interconnected world. Electromagnetic fields and waves are fundamental aspects of electromagnetism that permeate the universe, influencing everything from the behavior of charged particles to the propagation of light. One interesting fact is that electromagnetic fields are invisible but exert a powerful influence on the world around us. These fields can be visualized using field lines, which represent the direction and strength of the field at any given point. In a vacuum, electromagnetic waves travel at the speed of light, approximately 299,792,458 meters per second, making them the fastest known form of energy propagation. The electromagnetic spectrum encompasses a vast range of frequencies, from extremely low frequency, ELF waves used in communication with submarines, to gamma rays emitted by radioactive materials. Interestingly, the human body emits weak electromagnetic fields that can be detected using specialized equipment. Electromagnetic fields are also generated by electronic devices, power lines, and even the Earth's magnetic field. The study of electromagnetic fields has led to the development of technologies such as antennas, radar systems, and wireless communication networks. In the United States, the Federal Communications Commission, FCC, regulates the use of electromagnetic spectrum to ensure efficient and safe communication. Electromagnetic waves are used in various applications, including microwave ovens for cooking food, magnetic resonance imaging, MRI, for medical diagnosis, and satellite communication for global connectivity. The interaction of electromagnetic fields with matter gives rise to phenomena such as reflection, refraction, and diffraction, which are essential for understanding how waves propagate through different mediums. Overall, electromagnetic fields and waves are integral to our understanding of the natural world and underpin many technological advancements that shape our daily lives. Electromagnetic induction is a fascinating phenomenon that occurs when a changing magnetic field induces an electric current in a conductor. This principle, discovered by Michael Faraday in the 19th century, forms the basis for many technological applications, including electric generators and transformers. One interesting fact is that electromagnetic induction is the underlying principle behind the operation of power plants, where mechanical energy is converted into electrical energy through the rotation of turbines in a magnetic field. In the United States, the total electricity generation in 2020 was over 4 trillion kilowatt-hours, with renewable energy sources accounting for 20% of the total. Electromagnetic induction is also utilized in wireless charging technology, where electric vehicles and smartphones can be charged without the need for physical connections. The global wireless charging market is projected to reach over $27 billion by 2026, driven by the increasing adoption of electric vehicles and portable electronic devices. Another interesting application of electromagnetic induction is in electromagnetic compatibility, EMC testing, where electronic devices are evaluated for their ability to operate in electromagnetic environments without interference. The global EMC testing market is expected to grow at a compound annual growth rate of 6% from 2021 to 2026. Understanding electromagnetic induction is essential for the development of innovative technologies that rely on the generation and transmission of electrical energy through magnetic fields. Maxwell's equations are a set of 4 fundamental equations that describe the behavior of electric and magnetic fields. These equations were formulated by James Clerk Maxwell in the 19th century and revolutionized the field of electromagnetism. One interesting fact is that Maxwell's equations unify the theories of electricity and magnetism, showing that these two forces are interconnected and can be described by a set of mathematical equations. The equations are Gauss's law for magnetism, Faraday's law of electromagnetic induction, and Ampere's law with Maxwell's addition. These equations provide a comprehensive framework for understanding how electric and magnetic fields interact and propagate through space. In the United States, the National Science Foundation, NSF, invests over $800 million annually in research related to electromagnetism and other physical sciences. Maxwell's equations have been instrumental in the development of technologies such as antennas, radar systems, and wireless communication networks. The global market for electromagnetic simulation software, used to analyze electromagnetic fields and devices, is projected to reach over $2 billion by 2026. Understanding Maxwell's equations is essential for engineers and scientists working in fields such as telecommunications, electronics, and renewable energy. The impact of Maxwell's equations extends beyond the realm of physics, influencing advancements in various industries and shaping the way we harness electromagnetic forces for technological innovation. The electromagnetic spectrum encompasses a wide range of frequencies, from radio waves with long wavelengths to gamma rays with short wavelengths. Each region of the spectrum has unique properties and applications. For example, radio waves are used for communication, while microwaves are utilized in cooking and satellite communication. Infrared radiation is commonly employed in thermal imaging and remote controls, while visible light enables us to perceive the world around us. Ultraviolet radiation has applications in sterilization and fluorescence, while X-rays are used in medical imaging and security screening. Gamma rays, with the shortest wavelengths and highest frequencies, are produced by nuclear reactions and have applications in cancer treatment and sterilization. The electromagnetic spectrum is a valuable tool for scientists and engineers, allowing them to study and manipulate electromagnetic waves for various purposes. In the United States, the Federal Communications Commission, FCC, regulates the use of the electromagnetic spectrum to ensure efficient and safe communication. The global market for wireless communication technologies, which rely on the electromagnetic spectrum, is projected to reach over $700 billion by 2026. Understanding the electromagnetic spectrum is essential for the development of technologies that rely on wireless communication, remote sensing, and medical diagnostics. One exciting future trend in electromagnetism is the development of wireless power transfer technology. Researchers are exploring ways to wirelessly charge electronic devices over longer distances, paving the way for a world where charging cables are no longer needed. Another emerging trend is the use of metamaterials to manipulate electromagnetic waves in novel ways. These artificially engineered materials have unique properties that can bend light, create invisibility cloaks, and enhance antenna performance. In the field of quantum computing, scientists are investigating the use of superconducting qubits to harness the power of electromagnetism for ultra-fast calculations. The global market for wireless power transmission is projected to reach over $13 billion by 2026, driven by the increasing demand for convenient charging solutions. These advancements in electromagnetism hold the promise of transforming various industries and shaping the future of technology. The global market for electromagnetic simulation software is projected to reach over $2 billion by 2026. In the United States, the National Science Foundation invests over $800 million annually in research related to electromagnetism. The total electricity generation in the U.S. in 2020 was over 4 trillion kilowatt hours, with renewable energy sources accounting for 20% of the total. The wireless charging market is expected to reach over $27 billion by 2026, driven by the increasing adoption of electric vehicles and portable electronic devices. The global market for electromagnetic compatibility, EMC, testing is estimated to grow at a compound annual growth rate of 6% from 2021 to 2026. These statistics highlight the significant impact of electromagnetism on various industries, and the ongoing advancements in technology that leverage electromagnetic forces for innovation.